A full journal bearing with a journal of 75 mm diameter and a bearing of 75 mm length is subjected to a radial load of 2500 Newton at 400 rpm. The lubricant is SAE 30 at 75 degrees centigrade, having a viscosity of 16.5 into 10 power minus 3 kg per meter second. Radial clearance is 0.03 mm and eccentricity ratio of the bearing is 0.27 mm. So here it is a common data question. It consists two questions. Here the first question is Sommerfeld number is, and here the second question is minimum film thickness is. So coming to the solution, Sommerfeld number S is given by mu n by p into r by c whole square. Here mu is the dynamic viscosity of the fluid or lubricant, n is the speed of the bearing, p is pressure, the longitudinal pressure acting on the bearing, r is radius of the bearing, and c is the radial clearance between journal and bearing. So here all the values are known values except p, where p is the ratio of load to the area, longitudinal area, that is L into D. So here it is 2500 by 75 into 75, which gives a value of 0.44 Newton per mm square. So now substitute all the values here. Mu is given by 16.5 into 10 power minus 3 and n is given by 400 rpm, so that is by 60, and p is equal to 0.44 Newton per mm square. So just convert it into meter square, so that it is 10 power of 6, 0.44 into 10 power of 6, and radius of the bearing is equal to 75 by 2, that is 37.5 by radial clearance is 0.03. So from this equation we can get the Sommerfeld number is equal to 387 into 10 power of minus 3. So in the options, right option is C for the first question. And coming to the second question, minimum film thickness is. So minimum film thickness can be obtained from the equation eccentricity ratio E is equal to 1 minus h naught by c, where h naught is the minimum film thickness, and here eccentricity ratio is given as 0.27 mm, and h naught is film thickness and radial clearance is 0.03 mm. From this equation, minimum film thickness is equal to nearly 0.02 mm. So in the option, the right option is B. B is the right answer. The arc length voltage characteristic of a DC arc is given by the equation V is equal to 25 plus 4L, where V is the arc voltage in volts and L is the length in mm. The static volt ampere characteristic of the power source is approximated by a straight line with no load voltage of 80 volts and the short circuit current of a 600 amps. So here it is a linked answer question. It consists two questions in such a way that the second question answer depends on the first question. Here the first question is the optimum arc length is, and here the second question is the power utilized is. Here optimal arc length comes from the, or it gives the optimal power utilization. So optimal power utilization comes from differentiating the power equation with respect to L and equate it to 0. Here it is already given that the short circuit current, that is 600 amps, and output voltage V0 is given by 80 volts, and here the voltage DC arc is given by V is equal to 25 plus 4L, and power formula is given by VI, where I is equal to IS by V0 into V0 minus V, so that here V is equal to 25 plus 4L into IS is 600 by 80, and here V0 minus V0 is nothing but 80 minus 24 plus 4L. So from this equation we can get L value is equal to 4 mm. So this is the optimal arc length, and in the option the right option is C. C is the right answer for the first question. And coming to the second question, power utilized is. Here power utilization is equal to P is equal to 24 plus 4 into 4 into 600 by 80, and 80 minus 24 plus 4 into 4. So it gives a value of nearly 12 kilowatts, and in the option the right option is C. C is the right answer for the second question. A 250 mm long cantilever of 40 mm wide and 30 mm deep carries a uniformly distributed load. The maximum deflection in the cantilever not to exceed 0.5 mm and the Young's modulus is 70 kN per meter square. Here it is a linked answer question such a way that second question answer depends on the first question answer. Here the first question is calculate load per meter carrying by the beam. And here the options are 1.16 kN per meter, 1.61, 4.83 and 6.45 kN per meter. And the second question is maximum bending moment induced in the beam is. Here the options are 0.2, 0.4, 0.8 and 1.6. Here in the given question, a cantilever beam is carrying a uniformly distributed load throughout the length. So let us say this is W kN per meter over a length of 250 mm. So for this case, the maximum deflection in the beam not to exceed 0.5 mm. So generally the maximum deflection occurs in cantilever beam at the free end, and that is equal to WL power of 4 by 8 Ti and is given by 0.5 mm. So here L is a known value and E is a known value, and we will have to find out W, and here I is nothing but area moment of inertia and is equal to BD cube by 12, where B is the width of the beam and D is the depth of the beam. Here B is equal to 40 mm and D is 30 mm, so it is 40 into 30 cube by 12, and here E is 70 kN per meter square. That means E is equal to 70 into 10 cube Newton per mm square, and here L is equal to 250 mm. Now substitute all the values in the maximum deflection. Here we can get this is 250 power of 4 by 8 into 70 into 10 cube into 40 into 30 cube by 12. So which gives a value of, here it is equal to 0.5 mm, and from this equation we can get W, which is equal to 6.45 kilonewton per meter, or here it is 6.45 Newton per mm. So in the option, the right option is D. D is the right answer for first question. And coming to the second question, here maximum bending moment induced in the beam. So in case of cantilever beam, the maximum bending moment induced at the fixed side. So here at the fixed end, the maximum bending moment is equal to W into L by 2. So here W is 6.45 and L is 0.25 meters, and here into 0.25 by 2 is a perpendicular distance from the center of gravity of the beam. So here it gives a value of 0.2 kilonewton meter, and in the option the right option is A. A is the right answer.